So good morning and good afternoon, everyone. So this is the series of online technology meetings presented by EPIC, the European Photonic Industry Consortium. And the event today is dedicated to co-packaged optics for hyperscale data centers. So we'd like to remind you that this event is sponsored by several members of EPIC Consortium. Those are fibeReality, ficonTEC, OFS, axetris, IRIDIAN Spectral Technologies, SUS MicroOptics, Modulight, Nanoscribe, and Quantifi Photonics. And actually, we have members of those EPIC members in the room, and I would like to give them the chance to present themselves. So if we can start with maybe Quantifi Photonics, that is presented by Danny.
Thank you. I'm Dan Henley, Vice President of Sales for Quantifi Photonics. And our company offers a broad portfolio of test and measurement instruments. And we're very focused on developing instruments for very high density applications. At OFC this year, we released a PAM4 BERT in PXI and a 288 channel optical power meter to support the rollout of 800 gig co-packaged optical network infrastructure. So if you're testing considerations for high density co-packaged optical devices, we recently released a new white paper that you may be interested in reading, which is available on our website, quantifiedphotonics.com, or feel free to reach out to me via LinkedIn. My colleagues and I look forward to hearing from the panel today. Thank you.
Thank you. Thank you, Danny. And I believe we also have Jörg from Nanoscribe in the room.
Yes, I'm here. Hello, everybody. Nanoscribe is a 3D microprinting company. We have a very specific technology to do very precise, small micro-optical elements. I'll talk about this later and introduce you how we can enable a better coupling in onboard optics, co-packaged optics. Looking forward to the meeting.
Thank you very much, Jörg. Modulight. Well, maybe we don't have anyone from Modulight. So Modulight is a corporation for fully vertically integrated semiconductor, medical and laser applications. Maybe SUS MicroOptics, Wilfried. Would you say a few words?
Yes, thank you, Ivan. Yes, my name is Wilfried Noell. I'm from SUS MicroOptics. We are in the transceiver and telecom business in terms of making micro-optical elements. So we are making microlens arrays out of different materials. We've been doing this since over 20 years now, and we have some recent new products which will facilitate your packaging with integrated prisms. And I will show that later today in this event. Thank you, Ivan.
Thank you, Wilfried. Next one, next sponsor is IRIDIAN Spectral Technologies. Do we have a presenter in the room?
You bet, Ivan. It's Jason Polidor here. Nice to meet y'all. Good morning. So IRIDIAN's been, we're a custom optical filter manufacturer here in Ottawa, Canada. We've been doing this since 1998, initially focused largely on telecommunications components, but we are also involved over the last decade or so with a lot of applications for a lot of filters for datacom applications, including wavelength division multiplexing filters in the C band, O band, L band, very miniaturized small components. We can actually even pattern them as a single array. Also, we have etalon quality polishing capabilities and can coat etalons for applications such as integrated tunable laser assemblies. So we're all about custom optical thin film filters, and datacom is one of the large and growing areas that we're happy to participate in. So happy to hear about what EPIC members might need in terms of optical filters. Thanks.
Great. Great to have you, Jason, with us. And then axetris. Well, maybe I'll say a few words. Axetris is actually serves the
I'm here. I'm sorry. I'm a little bit late.
Go ahead.
Hello, everyone. Axetris is leading manufacturer of micro-optics, including micro-lenses and lens arrays, and also diffractive optical elements. As you know, our micro-optics enables all kinds of optical transceivers in communication market, and also some other sensing devices like quantum sensings and automotive 3D sensing lidars, etc. I think for today's meeting, like co-packaged optics or onboard optics, I guess you need more integration features. So we can do additional mechanical features or metallization for soldering, etc. on wafer level as well on our micro-optics products. So we can support you from basic micro-optics to sophisticated and complex integration feature added on micro-optics from small volume or like prototyping to mass production over the million chips per month we can deliver to you. So that's all I want to tell about axetris. Thank you, Ivan.
Okay, thank you too. Actually, we have John Earnhardt from OFS.
Good morning, good afternoon. This is John Earnhardt. I'm Director of Specialty Sales for OFS, based in Connecticut in the USA. Our business is specialty fibers across a wide range of applications, from telecom, datacom, to medical, aerospace, defense, sensing, fiber lasers. So a broad range of markets for specialty fibers. In addition, we are owned by Furukawa, and Furukawa, as many of you know, has the Fitel product line, either in terms of splicers or lasers. And I'll be talking a little bit later about both specialty fibers and lasers used in co-packaged optics. So looking forward to this discussion. Thank you.
Thank you very much, John. And of course, we couldn't leave without ficonTEC, and presented by Moritz today.
Yes, good afternoon, Ivan. Thank you. Probably most of you know ficonTEC already. So we consider ourselves as a solution provider for the high accuracy market, so mainly photonics. So photonics testing and assembly. And for photonics, I mean, it's a huge field. So ranging from the typical applications like the data center, like we hear today, doing all over the telecom and LiDAR business. So everything which is somehow related to optics and the high accuracies in the sub-micrometer range, which we need for the alignment, that's kind of our core business. And I'm happy in presenting you today a few of the ideas and developments which we have around that field. Thanks.
Thank you very much. And fibeReality, the last sponsor for today. And maybe I can just present it myself in a few words. So fibeReality is an independent research and consulting firm specializing in optical equipment markets, including telecom, datacom, consumer, auto, augmented reality, and more. So yeah, thank you very much to all the sponsors of today's event. And let's move on with the agenda. So we have a very exciting lineup of speakers today, and we'll see the presentations by Senko, Fraunhofer IZM, Huawei, OFS, the SUS MicroOptics, ficonTEC service, and Nanoscribe. But before apart from having the speakers from those named companies, we also have a large audience in the meeting today, and here are all the members of EPIC that are registered for the event today. And my colleague Panagiotis will maybe say a few words about it.
Sure, I will, Ivan. Just make me a favor, please. Can you please share the slides? We don't share your screen.
Okay.
So I can start speaking about it. So today we have, of course, co-packaged optics and hyperscale data centers. In the meantime, I hope Ivan will manage to share his screen. And the room, of course, is extra crowded. We have represented for all the value chain. Today the meeting is going to be one of the better networking events, since we will have the chance to connect everyone, ranging, and there we go, ranging from research and development up to the end users. We have, of course, in the room photonic integrated circuits companies and the packaging and supply and assembly companies. They are the key players, of course, in this event today. We have also people from optics and fiber optics, of course, and people from the materials and semiconductor manufacturing and software as well. And that's from me now, Ivan. I wish you all a business-rich and enjoyable online technology meeting. Thank you.
Thank you, Panos. So let's move ahead with the first presentation for today. And we'll start with a presentation by Tiger Ninomiya, the Technology and Innovation Manager from Senko Advanced Components. Tiger?
All right. I hope you're seeing my screen now.
Yes.
Okay, thank you very much. Thank you, Ivan, and everybody. And hello, everybody from all over the world. This is Tiger Ninomiya as representing Senko, and also later on I'll be speaking a little bit about Kobo. But let me focus on optical interconnect challenges in copax optics, as Senko's expertise is optical connectors and solutions. So let's review what is new with coming copax optics system. I'll touch base on fiber count increase. That's significant impact to how to arrange the fibers in and out, as well as one of the biggest changes we're foreseeing is external laser source. I think this is being addressed by Eric later on. And the phase density, this is also associated with the fiber counts increase, but we have to reserve spaces for laser sources, and also TRX channels are increasing. So we need to probably focus on what to do about it. And then, of course, fibers are inside now, optics are inside now. So you have to consider the way to solve the fiber routing inside the system as well. And as I addressed, one of the biggest changes is the fiber counts increase. So let's take an example of DR4 regular pluggable 400 gig optics to configure 12.8 terabits. So typical 32 port pluggable switch can have 8 fiber each per transceiver module. That adds up to 256 fibers. Let me do the same math to configure 51.2 terabit switch with CPO. CPO I illustrated earlier on. There are 16 modules embedded in on the same substrate of ASIC. And each one of them, if it's parallel optics, can have up to 64 fibers. That times 4. So it adds up to 24 fibers, 1,024 fibers. That's quadruple of what you are needing now. So what I'd like to address is the potential faceplate density is going to be an issue, as we need to have more fibers and also address external laser source spaces. So this is a chart I made to illustrate the fiber density and also connector fiber counts. So the y-axis, I plotted the fiber counts per connector. So LC duplex, so it's sitting here, similar to CS and SN. And the x-axis, I plotted the fiber density per 19-inch 1IU panel, a patch panel using adapters. So of course, MPO has better density over duplex types of connectors. And I also categorize in these 3 ways. So LC, CSSN are single fiber based connectors, although duplex, but single ferrule carries single fiber. So yellow one here, multi-fiber connectors, 1 row, so MPO 12, MPO 16, and also I address a little bit later, but the SNMT is a type of this. And multi-fiber 2 row, so 2 rows of 20, 2 rows of 12 and 16 to configure MPO 24 and 32. I believe this has some correlation to the optical fiber fiber optics insertion loss per connector. And the larger the fiber counts, it's challenging to maintain the lower loss. So the benefit of considering this kind of SNMT new connector is to maintain the good fiber density at the panel, but maintaining also the lower loss. So this is a quick comparison of the connector size, MPO and SNMT. You can see roughly half the size, and the configuring with the adapters, it can be a lot better than MPO 32 as well, even though SNMT carries 16 fiber. Right, let me switch to the next one. So other areas, Senko also supports some other technologies to save the space inside or behind the faceplate, fiber routing options, mid-board connectors, and also fiber routing, shuffle box, backplane connectors for probably like a machine learning, AI type of applications, also fiber to the chip solutions. This is more like a customized, but as you know, there are more fibers to be dealt or coupled to the chip. We probably need to come up with the great solutions to carry more fibers at once. And Senko is capable to provide these things, but we'd like to hear for what industries are needing to achieve the coaxial optics system. So let me switch a gear a little bit. So I'm also a board member at the consortium of onboard optics. So let me touch base on the active programs. So I'm chairing this coaxial optics working group. This has a specific scope to talk about or bring some technical guidance and standards for CPR implementations, focusing on optical connectivity and remote laser sources. So it's been delayed a lot, but we are foreseen to release the white paper on optical connectivity fairly soon, probably within June timeframe. And also we are expecting to bring the multiple fiber study type of white paper, how we can utilize such new technology. Okay. Another working group started last year is multi-mode waveguide interconnect system, MWIS. So this is to develop a technical guidance and standards for optical waveguide system replacing the copper trace on PCB, and we need to develop or demonstrate some kind of coupler, also waveguide itself, as well as the media adapter to achieve this. So if you are interested, let me go back one slide, but you can visit the onboardoptics.org and contact Melissa for any inquiries. If you are willing to join as a member, we are all really welcome. We have lots of things to discuss. So I think we can bring you a summary of what's going on within Kobo in more depth than this. With that, Ivan, I conclude my presentation.
Thanks a lot, Tiger. Thank you for this very informative presentation. So it's about time to have some questions for Tiger. There is anyone who would like to ask something?
Well, let me maybe ask you, Tiger. So the typical EPIC question: what do you expect from this meeting? What the other EPIC members could help you with?
Sure. So we're fully focused on passive components to couple the fibers or the connect the fibers, and there are a lot of different requirements we are hearing, like high temperature or reflow compatible, not only reflow, but we are hearing the high temperature operation as well. So I'd like to hear from like a system companies if they have any specific targeted environment to achieve the coaxial optics.
Okay, thank you.
Thank you. We have a question. I saw the hand waving before, but I saw it also in the chat now from Wilfried from Swiss MicroOptics.
Yes, thank you, Manas. In the last slide, Tiger, you showed the optical board with these red light beams, so to say, which show 90 degrees turn. So how are these 90-degree turns foreseen? Is there any preferred technology for this, or is that part of the COBO evaluation?
I think that part of the COBO's evaluation, we're open to any technology, I believe, and the purpose of turning the light, of course, is to catch the light from the big cell on the top of the PCB, and also transmit to the PD on the substrate. So as long as meeting the requirements, I think we're open to adopt any technologies, and we should be able to demonstrate a couple of different technologies as well.
Okay, thank you. Wow. Good.
Thanks a lot, Tiger. And we have one more question that comes from Tracy, our beloved Tracy. Hello, Tracy. I cannot hear you.
There we go. Hello, Panos, and hello, Tiger. It's good to see you again. As always, enjoyed your presentation, but I have one question. So you mentioned that you're looking at new ways of doing optical waveguide coupling. Does that include some of the newer waveguides, such as those made by polymers?
Yes, I think polymer is one of the good candidates for this one. And so to answer the other question, probably it has to be compatible with the waveguide materials or the mode field diameters and so on. So I believe the main focus is to utilize the polymer waveguide to this one.
I'm sorry, I missed that last bit. What was the last bit?
Oh,
to utilize?
Utilize the polymer waveguide for this demonstration, most likely.
Oh, that's wonderful. Thank you so much.
Thank you,
That
Tracy.
sounds interesting, Tracy, no? So if we don't have any other question, I would like to pass to the next speaker then. It's Tolga and Tekin from Fraunhofer IZM.
Can you hear me?
Yes, we can.
And see also, thank you very much for the invite. And you can see also my screen, hopefully, in full format.
Crystal clear. You can start speaking.
Perfect. So I'm with Fraunhofer IZM in Berlin. So allow me to give one slide overview what we have been doing in the last decade in the topic of next generation computing and data center applications using photonic interconnects. We started with Foxtrot project, which has been the flagship, where we concentrated on rack-to-rack, board-to-board, chip-to-chip optical communications. Then in L3 matrix, we have been focusing on co-packaging technologies as a platform. And recently and currently, we are working on Mastrad, where we concentrate on mass manufacturing data center transceivers. I hope Moritz can talk more on that mass manufacturing items. So as Fraunhofer, we contributed most likely in the system design and concept, photonic RF component design, signal integrity board design, silicon photonics interposer development with through silicon via technologies, 3D integration technologies based on flip chip assembly, and finalized several co-packages, and then also evaluated those components and systems and benchmarked them. Tiger directly started with the topic. Allow me to provide some background info on data center network topology and where the limitations coming from. We know all the structure, this spine leaf structures in data centers, 70%, more than 70% of the traffic stays inside the data center. In the recent projects, we have been focusing on Foxtrot within that racks, and in L3 matrix, this switching area, and Mustard, we are focusing on single mode links everywhere. So the focus should be, or the interfaces should allow us to have enough capability and symmetry in order to connect all the nodes over there. So that means we need higher Ethernet switch radix, which enables this kind of scaling. For the time being, the SerDes is actually becoming kind of limiting factor within the entire scaling. Today, 256 elements are there, and PGA is not a limit, but the port count is becoming, and the routing becoming the main challenge over there. So as we know, in data center network, the switch bandwidth and transceiver bandwidths are following to each other. So again, here we see on the left-hand side switch bandwidth 51, 52 terabit switches with chip radix 500, SerDes speed 100G. It can be later on 200G with 256, and the port numbers and port speeds. So what we observe is there the SerDes power consumption increasing with the bit rate. So that's again identified is an identified bottleneck over there. If we take a look at the cost considerations, typical transceiver costs, we aim to have $1 per gigabit per second, considering single mode transceivers. Given the 32 ports and even 64 ports, we can assume 10-13K basically cost on the optics. And if you consider the entire data center, the entire transceiver cost will be somehow above $50 million. So further, why we would like to decouple the IOs from the optical logic, since our main intention is to reduce the power consumption by decoupling the IOs from the switch ASIC. At the left-hand side, we see the switch ASIC, such an example, 25 tera switch ASIC. It's consuming 600 watt, and 1/3 of those power is directly linked to the SerDes power consumption. If we can actually reduce the SerDes power consumption by introducing the disaggregation of IOs in the optical domain, we can reduce the SerDes power consumption down to 40 watt. And by doing so, we can also increase the link reach. And here we see 1 dB penalty, or there 1 dB loss. Will that interconnect cost instead of 12 dB? So I think moving from mid-reach, long-reach optical electrical connections, we then have ultra short reach, and by doing so, reducing the power consumption at the SerDes, but in the other hand, means of optics, we reach larger distances. In the L3 matrix project, we have been focusing on those kind of 25 terabit switches with co-packaged optics using 2D transceiver array as shown at the right-hand side, consisting of based on silicon photonics with integrated 3.5 materials. In the next slide here, you can see some more details. It has been addressing up to 256 lanes. It included integrated lasers by bonding 3.5 layer on silicon photonics based on Mach-Zehnder configuration to have the right modulations over there. It was basically relying on AMS 35 nanometer technology, 350 nanometer technology. Here in that slide, we see again the co-package, how it was connected. the fiber array to the fiber array coupled directly by using micro lens arrays. I think our colleague Wilfried will more talk about these 2D lens arrays in his presentations, combined with silicon photonics integrated 3.5s and directly attached next to the switch ASIC. We have been demonstrating our results at the OFC, and I think if you would like to have some more details on that, my colleagues from UCL, IBM, Valencia, Bright Photonics, AMS, and Dust Photonics will be happy to provide some more details. Thank you very much.
Thank you, Tolga.
Yes,
thank you for the great talk. And as always, Fraunhofer sets the technology bar very high for all of us. We have already a question in the room from Tuan, Synopsis.
Hey, Tolga, good to see you.
Hi, Tuan, my pleasure.
In slide 6, you showed, let's say, that power consumption difference between electrical high-speed SerDes I/O and replacing that by optical I/O.
Yes.
Is this based on, I have two questions. Is this based on, let's say, calculations or based on true measurements? And second, does it take into account the power consumption from the laser?
So the power consumption from the laser is not included here. It's all about this 25 tera switch ASIC power consumption, which is about 600 watt at all, right? Considering also the SerDes, 256 SerDes elements on that. And if we move again to disaggregation in the optical domain, since we are allowed to use ultra short links, we can reduce the SerDes power consumption actually from 180 to 40 watt. And by doing so, saving energy, which we can use for new functionalities for 52 tera switches. Now 52 tera switches have been announced, right? With adding some new functionalities. Actually, this in this node, that's unfortunately the main calculation for 7 nanometer CMOS ASIC node. I think that's roughly the thumb rule, let me say in that way. Sure, our industrial partners have been calculating in more detail and providing us with those numbers. I think that will be sure different in different use cases and business cases and so on. Right?
So okay, so more or less what you're saying here is if I replace the longer distance SerDes by short reach SerDes, I can save 140 watts, and those 140 watts I can now use for functions in the switch ASIC because
yes.
I no longer, okay. But
yes.
if you look at the overall power consumption, including driving, let's say the I/O, then actually the optical I/O chiplet also requires power consumption to function.
That's for sure. At the end of the day, we do have all the transceivers also, right? Yep. So in the transceivers power consumption with respect to the entire data center is in the range of 5% almost, right? Maximum.
Yeah. Yep.
Not at all. So, but what we save here is the power in the switch ASIC with respect to SerDes.
Yeah, understood. Okay. No, thanks for the clarification.
Thank you. And we have also a question from Eric Bernier from Huawei.
Yeah, if you go to page 9 of your presentation and I look at your 3D demonstrator,
yes,
I'm trying to understand where the switch chip is.
So the switch will be basically down here.
Okay, on the interposer.
Yes, I think within that kind of European projects, the resources to develop a switch ASIC is not in it. So that's why it's kind of mimicked with the interfaces based on the given switch dimensions and pin locations. Thank you.
Yeah, okay, understood. Now you're saying you would put the basically a square in the center that has detectors. Do you do modulators, or those are lasers?
So those are actually integrated modulators with 3.5 hybrid bonded lasers on that.
Yeah, and did you look at the terminals for that solution?
Pardon me?
Did you look at the terminals for that solution? Did you do thermal simulations to see if the laser would have good performance and
yes, that has been surely
displayed in the chip?
The integration of lasers directly on silicon is the main challenge, right? So I think apart from that, I think then we introduce also the cooling elements that respect the backside of the chip, and also decoupled thermally from the Mach sender. So since its Mach sender is less, let's say, sensitive compared to the ring resonator based modulators, right?
Well, I was more concerned by the switch chip itself generating a lot of heat, and so you're in a very warm environment in the middle of that chip.
I think that's for sure. That's for sure. In that given constellation, we have been focusing on the optical domain only.
Yeah.
We were not able to test it with the real ASIC switch.
Yeah, that's pretty good to have such a big array connected to a switch.
Actually, the intention has been to provide a platform which is capable to do the entire co-packaging and the disaggregation in the optical domain with such kind of configuration. So by doing so, we demonstrated the capability of such 2D transceiver arrays combined with 2D lens arrays and connected to the entire drivers and receivers over there. Thank you.
Thank you, Tolga. Tracy, do you have another question?
We cannot hear you, Tracy. You are muted. You are still muted. Yes.
There we go. Okay, I'm so sorry. Thank you. Tolga, very good presentation. Really appreciated it. And, it seems to make perfect sense. So initially it was the density of the connectors on the faceplate, the density of the fibers, and then, how do we connect to the PIC? But now it's the SerDes. What other problems do you think that we're going to see? I mean, it makes sense that as we increase the density, we're going to see downstream changes that must occur. So in addition to the SerDes, what else do you think is the kind of the next focus of improvement?
I think electronics is sure working on that, on switch technologies, new ASIC based on new CMOS nodes. I think for the timing that we have to focus to identify from photonic optical domain point of view, which type of configuration makes sense. Shall we directly integrate lasers in those transceivers, or shall we have, let's say, off the module lasers? So I think those are the critical questions, and sure, we have to really understand if we can meet the costs by doing so, right? And reliability.
The cost of power, yes. Anything new on the power horizon? Any new solutions that look like additional things that may help reduce the power in addition to what you've mentioned?
As I mentioned, the contribution from photonic transceivers in the entire data center power consumption is less than 5%. So, and even 2%. What we can achieve is mainly by introducing new photonic interconnects. We change somehow the entire topology, and by doing so, also in the protocol domain, in all domains, introducing some new features by using WDM. That will allow us to have more flexibility in the ASIC development. So I think that will be my understanding.
That's a great answer. Thank you so much, Tolga. Appreciate it.
Thank you. Appreciate it.
Thank you, Tolga. Very quick question, maybe Antonio?
Yeah, I was curious about the lenses you show in the last slide to connect to couple the light from the fibers. Do you know which material do you use? And
those are silicon. I think I'm sure Wilfried can give some more details how those bulk optical elements 2D can be fabricated and what are the possibilities over there. But I think it's based on silicon. Sure.
Mm-hmm.
Thank you.
Great. Exciting. It's always great when we're on the fringe with research. So the next presentation comes from Huawei, and Eric Beignet, the leader of advanced photonics at Huawei, will share his thoughts.
Okay, hello everyone. You must be seeing my slides now.
Yes, that's good.
Perfect, thank you. So I'm just gonna, I wanted to give you a short introduction about the projects that are going on to a standard organization called IPAC about co-packaged optics. So that's what I'll be talking about. Trying to change my slides. Okay, perfect. Okay, so just for those who don't know HiSilicon Optoelectronics is a division of Huawei. It's got 1,200 employees. We have global R&D teams. We have teams in Belgium, in Germany, in UK, in Canada, in Japan, and also in Wuhan and Shenzhen. We have revenues of about 1.5 billion US dollars per year, with the patents portfolio about 1,300 patents. So what we do, we develop the components, the photonic optical components that go into the larger systems. So traditionally we've done the lasers, the modulators, and the modules that would go into more of the Huawei telecom equipment. And we're in the midst of diversifying our offering by offering sensors like LiDARs and other type of sensor like that to the time of flight sensor, things like this, in order to expand our business. One of the things we're involved in at Huawei Optoelectronics, HiSilicon Optoelectronics, is the IPAC. The IPAC is the International Photonics Electronic Company. We're an open standard organization based in Switzerland. There is 31 members. I've got the member listed here on the right of the slide. And we focus on optoelectronic industry, like optical chips, optical electronic components, optical modules for 5G, Internet of Things, and AI. I think there's so you have to disregard it. I think there was some leftover from old slides at the bottom here. So the first thing I wanted to talk about, one of the projects at IPAC that we have is the standard research report on 100T optical I/O standards. And basically what it's about is we've been talking in the 3.2 terabits per second optical elements that people are talking about in those forums or the OIF or the IEEE. It's all targeted for a switch chip of 50 terabits per second. And we know that at 50 terabits per second, this is a first introduction to the industry for the CPO, the co-packaged optics. And we also know that the 50 terabit switch can survive and they can work properly with our current module-based architecture, and we'll just do the same but faster. What the consensus around the industry is that at 100 terabit switch for a switch chip like that kind of bandwidth, then it becomes impossible to move the data electronically with the SerDes without basically consuming the entire power budget for the switch chip in just in order to move the data in and out if you're going to use electronic long reach SerDes. So this is at 100T, this is where the co-packaged optics really becomes needed. But something you have to look at is if you look at it as a module perspective, I don't think it's possible to double the number of modules, right? We normally want to try to minimize number of modules that are on a single package because that's a reliability issue. And also it becomes harder to package. And if your lanes are still very long, right, then those SIRDAS at the corner of the chip needs to still be very strong, and you don't have a lot of savings. So going forward, right, there's going to be a lot of push in order to increase the density and the capacity for the co-packaged optics, 6.4 or 12.8 terabit per second, right? Looking at 200 gigabits per second per fiber coming out of each modules, minimum, probably going WDM, multiple wavelengths per fiber, just to have higher density, higher footprint. And if you look at the die, let's say here, the photonic die or the photonic engine is the little gray block here, right? So we also have to increase the density of bandwidth per second for the same type of area of the photonics. So there's lots of challenge going forward, right? We'll need to input more optical power into those engines, right? So there's lots of good progress in our technology, in the development, the discussion, and the standards. But ultimately, we need new technology, and that's required. And that's why we're doing, at the IPAC, we're doing a research report to look at those issues, where we're going to look at network system architectures. We're going to look at evolution of the optoelectronic and the packaging, right? So the modulator themselves needs to be a quarter of the size. The packaging needs to be a lot more advanced, right? We need to support high power, and we need to reduce loss ultimately. I want to look at photonic device, process evolution, roadmap, to the channel density for improvement, and the pluggable versus non-pluggable CPO. All of these CPO modules that people are talking about today, they are assuming a connector, so we can basically, because it's easier for our supply chain and assembly chains, to just keep that connector on the back of the small optical module. However, if we increase density and we want to reduce the power requirement on the SIRDAS, we need to get rid of that connector, and that's something we want to look at here. The project started around September timeframe of 2021, and it's going to go on throughout this year, where we're looking for submissions into IPAC. Everybody's welcome to become a member here. We are, we are looking for the industry to push forward on those issues. Right. So throughout this year, we're looking at getting contribution. I'm the editor of the white paper, so we'll put all the parts together, and we are targeting to issue a document by the end of this year for ballot, and having the full research report published in Q2 of 2023. So that's for the first project on OIO research, right? Now, the other thing that's going on into the IPAC standard is form factor. We call it the form factor standardization, where we are looking at standardizing a specific form factor for the external laser source. If we look at the different laser sources that are possible from the OIF documents, there is multiple ways to do it, right? So I think Kobo is looking at central board laser. People have talked about faceplate pluggable, but faceplate with a jumper cable, or back blind connector, or even we're looking at very large and powerful lasers that could sit at the bottom of the rack and be water cooled, for example, right? So we can really provide a lot of photons for the modulator ultimately. The form factor research that we're talking about is about the 2A type. It's going to be a back blind connector and faceplate pluggable laser. And one thing we're looking at in more details, we're looking at a common arrangement where we're going to use a QSFP-DD or OSFP type form factor so that we don't really need to change the faceplate organization. We're looking at using a blind mate connector with a single ferrule. We think it's a reliability issue. We want to just have to deal with a single ferrule and just 2 pins for that connections. Spring-loaded ferrule to avoid overloading the power on the connector as you insert and remove the modules. Seamless management, conventional power, and will provide high reliability, operational simplicity, maintainability, serviceability, and stability. That's the scope of the project, looking at electrical specifications, optical specification, wavelength, lane assignments, optical characteristics, power object, etc., electronics and optical connector, mechanical, seamless interface. In this case, we're probably going to use what's being defined. My group is doing a big push in defining what's going to be done at OIF for the seamless, but we're going to be using it in IPEC and our environmental specification. Project just started a month ago, and it's supposed to go on and having a full specification published by early next year. That's a bit faster because it doesn't cover as much ground as the optical or the research paper. But again, here, right, we're looking at more people to participate so that we can get something that everybody wants to use, and that's it for that project. So thank you very much. If you have any questions or want to participate or want to contribute, we can even come. Like we can invite you to the discussion. You can have a try before you become a member. Right? Just give me send me an email. I'd be happy to include you in those discussions. Thank you.
Thank you, Eric. Thanks a lot. And we already have some questions for you. The first one comes from Wilfried from SUSE MicroOptics. Wilfried, would be great if you ask the question yourself.
Thank you, Panos. Yeah, I have actually a few questions. You saw more technologically questions. So, did you decide already? Because you said the lasers will be off board, which is quite an interesting approach, which makes a lot of things probably easier, but there's less integration. So, what about other points like it will be PAM4 or coarse or dense wavelengths multiplexing? Do you know already how many channels? And then my other question is a little bit more. There's this 5G situation between Huawei and the US. So is this going to be affected here or somehow? How is this going to be? Are you working with Kobo on this or are you excluded there completely? Or I don't know if you can comment on this because I know it's a very sensitive topic. So
okay, well, it's very easy. So standardization, publications, research work is excluded from Department of Commerce rules of the US government. So there's no problem. We can go and because they're public forum, right? We're not doing anything we're doing everything in the open. So that's no problem.
That's a good news.
Yeah. And like coming here for me to present today, it's a public forum. There's no problem, right? So it's all kosher, it's all good. So that I think that's fine. I mean, in terms of business, right? Of course, it's very hard for Huawei to go and purchase anything from the US, right? But China is a big market and it's growing, and the business is just flourishing that way. I don't think that's my 2 cents on that part, and I don't think I can comment very much more than that. In terms of PAM4 or PAM6 or PAM8, if you follow the IEEE 823D group that's being discussed right now, there's lots of people that discuss different PAMs, and it doesn't look like there is. If you do PAM6 or PAM8, you need more FEC. You need more further correction because your eyes is smaller and therefore it's going to be more closed and be harder to recover. You'll need more FFEs, right, to just reopen eyes. And it doesn't look like there is a lot of gain because you have, you have to derate everything. So there is not a lot of gain into going from PAM4 to PAM6 at this point. And so my conclusion from that is we're going to be at PAM4 for a long time at this point, right? Yeah, but the good benefit of move and to move to your other question, why you want to move the laser outside, is because, as I discussed, we're trying to increase the bandwidth density of those optical engines, and the laser themselves, even if they're integrated, they take space. And even and right now it's possible to use a micro, like if you look, Intel's presented papers at OFC, you can go look it up, right? But if you just take a picture from their paper and you see how many microring they have in the laser space, you can see that they can do about a 4 terabit per second modules in the space that's required for an optical engine. Well, we need to double and quadruple it. So something's going to go, and it's going to have to be the laser, and we can move the laser outside.
So
the penalty for moving the laser outside is loss. So we need very low loss coupling.
What is your take on coherent? Is it still too expensive, or are the DSPs an issue there, or what is the or do you think it's more than PAM4 versus coherent? Or
that's a good question. It's the DSP right now, or it's the cost per bit. How much? It's picojoule per bits. So we're trying to go to minimum picojoule per bits. We're not trying to go very far, right? Coherent, right now, I think for the next 5 years, the break-even point is about 10 kilometers. If you go beyond 10 kilometers, you want to go coherent. It's my view. If you want to go below, you probably want to go IMDD. Unless we find a way to do coherent very cheaply in terms of power, in terms of numerical, computations. So that's, of course, this is an evolution, right? So you have to keep your hand on it, right? That threshold may move a bit, but at this point, I think the threshold is around 10.
Okay, thank you. Yeah, that's the feedback I basically got at OFC, also from the other companies. So it's pretty coherent. Okay, thank you.
Yeah.
Thank you. Thanks a lot. That sounds to be a very interesting discussion, but we still have more questions. The next question comes from Nanoscribe, from our epic friend Jörg. Jörg?
Panos, nice to see you. Eric, nice talk. I have a basic questions. You showed this empty ferrule connector. You want to bring a lot of PM polarized light to the OEs, as far as I understand. So will you reduce the pitch? Will there be more dense fiber density in the ferrule, or what is the next step you see in your standardization?
Well, I think there is a metric, right, which is basically constant in the industry right now. It's like cost per fiber alignment. So the more fiber you have, the more cost you got, right? And we don't want to increase cost. So ultimately, we'll need to reduce the number of fiber, right? I don't think we're there yet for like that generation of CPO, but I think, going WDM, like right now we're talking 4 wavelengths, but 8 or 16 wavelengths, I think that's the way to go, right? In order to reduce cost, really. In, PM alignment, number of PM fiber alignments, it's also reduced, adding a lot of cost, right? And so that's where we'll need to reduce it.
Thank you. Thanks, Jörg, for the question. Thanks, Eric, for the answer. I have 2 more questions for you. I would like to ask you to try to answer a little bit quickly because we have to go on, but I want to give the chance to the people to ask their questions. So the next question comes from Tiger Ninomiya. I hope I'm pronouncing it well, from Senko, the speaker.
Yes.
Tiger.
Thank you. Thank you, Eric. Great presentation. A quick question about the pluggable ELSFP module that's under development in by the IPEC. But is there any consideration of how to maintenance the empty ferrule interface? So for such high power laser source, like inspection, cleaning, and design to make it easier?
Well, this is something that's being looked at by the group right now. I don't think that's the project just started in the IPEC. They have not brought in that issue yet, so I not really I cannot really comment with respect to the IPEC project. But it's definitely something that's important, right? We're talking, the lower power laser coming into an optical engine would be 18 dBm, right? And we're talking going to about 24 dBm. And I've done contribution in the OIF that shows, connecting a laser at 20 dBm can pulverize just the plastic ferrule, or like some part of plastic ferrule, like not the fiber core in glass itself, but anything that's around it. If you have too much power going there, right? So you can imagine if you have a little piece of dust of fiber, it will just pulverize and it will be, will destroy basically the connection. So yes, cleaning is definitely super important, right? And I know you guys are working on it, so I'm waiting for your solutions. But yeah, I cannot recommend beyond that point here.
Thank you.
There you go. We have connected now again. And Tracy, of course, we cannot refuse your question. Unmute and go.
Thank you so much, Panos. Very interesting talk, Eric. So as I was listening to you, and some of your comments about, it's hard to move the data electronically. Yes, it is, and it takes a lot of power. And one of the biggest problems within these data centers is power, and resultantly, how do you cool them? So looking ahead, maybe 10 years or more, with combine that with the moving the lasers down to the bottom of the rack, do you ever think that we're going to get to the point where this is going to be pure optical, where we're looking at an optical switch as opposed to, we've been doing optical switches for over 20 years. Do you think that we're going to start moving optical switching into the data centers?
Well, since I worked maybe 5 years of my life building switches, I probably have some still standing record on the size of the high-speed switch that we're actually working in. So, but the problem is really in what you like. I think the problem in adopting a photonic switch is to move away from a technology that we know we can extend. The risk is lower on electronic. We've built electronic switch. We've got learning. We've got knowledge that spans 30, 40 years, right? Whereas when we go into photonic switch, first of all, we get something that can handle very, very large flow, but not very well the packet size, right? And we also get to a brand new technology with a lot of things we don't know about. So there is a lot more risk, right? So I think people are going to stick with the electronic switch for as long as they can. When we talk about, so that's the first part of my question. When we talk about the power, and I think what's important to realize is what takes a lot of power in a data center is the hard drives and the CPU. Like when we talk about those switches that need a lot of bandwidth, they don't really make a big difference, right? But what really makes a huge difference, the power, like basically for a switch chip, we have a power budget. We cannot really ask this chip itself to consume more than something like let's say 600 watts, right? It's still a very large number, right? So it's what are you going to do with that 600 watts, right? And if we're going to spend a lot of that 600 watts on CERDAS, then we don't have a lot to do the switching itself, right? And so at this point, what we're trying to do is move a lot of that power outside of the switch chip, right? And that's what the CPO does, right? It moves the power away from the switching. I think, in a whole, as an architecture, as a system, because we have more loss from the external laser, we will consume more power. In the end, we will consume more power as a system. But the switch chip itself is going to, basically, we're going to remove power from the switch chip power budget itself. And that's going to allow us to attain more performance in those chips. And that's what we're trying to achieve here. It's not really to save the planet, but to make our design possible. That's why we're doing it.
I mean, certainly for the EO, for the individual flows, you need EO at some point. So I was just wondering if you thought that this could, I mean, and this is a discussion that we can have later, but very interesting talk. I really appreciated your information and certainly the answers that you just gave.
Yeah, you know, and if somebody wants to build a photonic switch, I'm all with you. I'll go and do more switch, no? I'll be very happy. You know, I'm just waiting for a customer. My designs are ready.
Yeah, no, it's possible, but I mean, you've got to get down to the individual EO if you're looking at the packets. But if you can aggregate those packets, then you can change the system, you know.
Oh yeah, like we have, I've got papers of architecture where we have like photonic packets, or obviously a big aggregation of packets where we aggregate the flows and manage large queues and stuff like that. Right? There's a lot of tricks you can play in, but you know, yeah, but I think there is a lot more teaching that needs to happen in industry as well. I know I saw some paper at the UFC, and you know, like the understanding of all the switch and what are the limitations and all the scaling and what can happen to, like, depending on which choice you make. I don't think that's well understood, even with that new generation of researcher coming in. And we know that's we're just starting over again. Like at some point we know.
Perfect. Thank you, Eric. I'm sorry. Thank you, Tracy, and thank you, Eric. I'm sorry for interrupting, but we still have, I mean, your discussion triggered more questions. So there is another one. I would like to give him the floor. Let's try to be quick, and then we'll go to the next speaker. So Tolga Tekin from Fraunhofer AZM.
So it's sure side topic is optical switching in data center, but allow me to comment on that based on our Foxtrot project, where we have been working also on optical switching functionalities inside the rack. So I think it's possible for sure, but it requires the entire adaptation of protocols by allowing WDM functionalities introduced to the protocols. So it's not changing directly from electronic switches to optical switches. It requires more than that also in the protocol, and the entire control domain, it should be adapted. Thank you.
Good, thank you.
Thanks a lot. Thanks a lot for the statement, Tolga, and thanks a lot, Eric. Maybe it's a good time, a good moment to go to our next speaker. And our next speaker, just give me a moment, is John Earnhardt from OFS. John, are you ready to share your screen?
Yep.
Hello, John. Perfect. The floor is yours.
Just bear with me as I get set up.
Yeah, you can just.
Yeah, hold on 1 minute.
We did it correctly half an hour ago. We can do it again, no?
Yeah.
There you go. Something's moving. Full screen
Let
mode.
me go to full screen. Excuse me.
Yeah.
Okay. All set.
Seems to me that needs a little bit more time.
Not seeing it yet.
We've seen it, but it's stuck. At least my screen. We can go to the next speaker. In the meantime, we try to solve this one. Is that okay, John?
Sure, that's fine.
Okay, Ivan, can you please introduce the next speaker?
Yeah, sure. Wilfried, could we ask you to start your presentation instead? So this is Wilfried Noell from SUSE MicroOptics.
Okay, wait, give me a sec. I'm ready and go. So
thank you, Wilfried. Yeah, the floor is yours.
Thank you very much. So as I mentioned earlier in the introduction, I'm in the doing the sponsoring section. We are from SUSE MicroOptics, and we make micro optics since 20 years. And today I want to talk about particular solutions that could make your co-packaging easier. So it's like we all know, there is a big, it's not only optics, it's also packaging. So the 85% of a transceiver is still packaging. And with co-packaging optics, I think the emphasis will be even more on packaging than just on the optics. So the optics will be just whatever you can get, but the packaging is the issue. So that we also saw that very nicely in the Kobo presentation and from Huawei. So this is very evident that the packaging is important. So we are from Neuchâtel in Switzerland, close to the lake, very nice location. We have several clean rooms now for 200mm wafer processing. We've been doing this since 1998. We are very big in data and telecom. And also recently we moved into automotive like 3 years ago. So we're fully IATF compliant and certified. That means we can also deliver to LiDAR, which is getting very similar to so the infrastructure and LiDAR, the technological infrastructure becomes very similar to the one of data and telecom. So we've been doing data and telecom since many years. As I said, we also are in the semiconductor and medical field with illumination optics. And what we do for data and telecom is mostly collimation and refocusing optics based in fused silica and silicon. So you can pick the material, whatever you prefer. Some people prefer silicon because of for high numerical apertures of the light source, and fused silica is nice because it's easier to package when you use UV glue or something. So this is typically more a question about how stable your system is or how you assemble these things, which material is better. So we learned that fused silica is easy for two reasons. Like I said already, the UV glue is easier to use, and the epoxies. And the other reason is actually the change of the material properties with temperature are very small. So refractive index change and expansion coefficients are very small, whereas silicon, it's a little bit different. It has a larger expansion coefficient, and also the N over dt, so the change of refractive index is a little larger. But because it has a higher refractive index, it's more suitable for high NA optics. So it has its pros, its cons. And in terms of form factors, we offer lenses on the front side and the back side. We are offering lenses embedded, or we call them recessed. So that means you have here a flat top. I'm going to talk about this. We offer all types of fiducials, obviously, and that makes your packaging much easier. Also trenches on the backside. So why is it coming in handy? So in particular, for if you have grading couplers or if you have a little mirror down here, there are different ways of getting the light out of your waveguide. Sometimes the grading is on the same side, sometimes on the opposite side of the substrate. So there are lots of different configurations. This is just a schematic for one possible way of getting the light out of your PIC. And so there's typically an air gap here, so that, and then in order to either let the beam expand a little bit or to avoid a glue interface to your whatever coupling surface you have here. And especially if it's not a grading coupler, it might be easier to have this air gap there. And these trenches that are done at the same time, they can act as glue stops or glue pockets actually. And in general, you have a collimated beam, but you can also sometimes refocus directly to your next optical element. And what we've been recently developing, and it's becoming more and more serious as a product, actually we have one client already, is these integrated mirrors, where you can have a 90 degrees turn of your light. And so you have this micro lens down here, which kind of either collimates or refocus the light to the next level. And we have a more generic design now, which we can also, which we are now setting up so that we can give them to different companies for demonstrations, for tests. So it's a fully integrated way of a 90 degrees step here. You see here the zoom in, and you have here then the 90 degrees turn, and at the top you have your micro lens. So here's your micro lens, so that either collimates. So we made two designs more generic designs, where one is focusing the beam here outside the microlens, and the other has a more collimated approach. So it depends a little bit on what you do. So we had to start with some type of design. So for our generic design, so this is the one we chose. And it can be used maybe for some applications and for testing definitely. And our technology has the option to change the angles of these different facets, and also the depths that you see here of the different elements can be changed. And obviously, since we do the microlens in a separate process, we can have all types of microlenses and microlens arrays on that side. So this is a little bit overview of all the packaging features. So as I said before, we have these simple lenses. They can be just glued to fused silica fiber or to some type of edge emitter. It can be directly attached. We can provide the corresponding air coating. This recess that I mentioned earlier, this is typically used to assemble an isolator or prism. And I already talked about the grading type PIC. And we also offer gold tin soda pads, so you can use reflow processes. And we can also do some additional feature by deep reactive ion etching. So if you need some passive alignment or more or less passive pre-alignment, we can etch trenches or circles into the silicon lenses mostly. And I'd like to thank you for your time, and I'm curious and open for questions.
Great, great talk, Wilfried, as always. Thank you very much. In this topic, what would the other EPIC members be? Yeah, who could be your potential partners, and what would you?
So we are really looking forward to integrate this somewhere. So we're talking with some companies already about this. But really, we need more guidelines. I mean, Eric mentioned that there are standards being setting up, and also Tolga mentioned this. So I'm very curious about these standards. We are not part of COBO, we're not part of IPEC, so maybe we should. So it would be very interesting for us to know where this road is going. There's going to be a standard. And I think there's some people unmuted. The background. And anyway, so for us, it's important to know, the big EPIC question is there, how can we be part of the standardization with our technology? So if there's a standard that is not easy to manufacture, it would be difficult. We can offer, of course, samples and to try this, and we're very open. A lot of our discussions with our clients are to develop new features, of course, in prototyping. So we like to offer prototypes for tests. But we need to know where the road is going, what features are expected from us. And because this can be quite a lengthy development. So the part that you see here, that took us almost a year to develop. And if so it's readily available now. We showed it already at OFC, and we have very good feedback. The question is now, what's next? So is this the right form factor, or are we going in the completely wrong direction? What is the situation from the transceivers and the integrators companies?
All right. Thank you, Wilfried. So please make sure you stay until the discussion we have, the informal discussion we have after the event. I'm sure there will be people who can answer those questions. And so we have a question from Costa Gurgov from Engage Photonics. Costa?
That is correct. I would like to ask, are the optical shapes that you can fabricate on the substrate, what kind of limitations are there? Can you fabricate A-spheres or asymmetrical shapes? And can they be on both sides of the substrate?
Yes, so we can make A-spheres on both sides, front and back side. We can have trenches. We can combine trenches with A-spheres. We can even, didn't show that today, we can even do add gratings or diffractive optical elements. So this is, all of this is no problem for us. We've been doing this since many years. in volume products. I think I have a slide on the diffractive optics. No, I took it out. So we also do diffractive optics. A-spheres we do every day. We also do A-spheres with very high conic values, so -10 or -12 or this. We can do this. There's no limitation. And we can combine all these different features that you see here in a single element, front and back side.
Very nice. What is the typical surface quality of the optical surfaces or surface roughness?
So there's the roughness, there's the RMS error of the shape deviation, which can be anything between, let's say, 5 and 100 nanometers, depends on the lens height. So typically it's much less than 50 nanometers, between 10 and 30 nanometers. That's for the shape deviation. For roughness, we are in the single-digit nanometers. So this is pretty standard for this technology of our process. So this is not
understood.
There's no diamond machining involved or anything which has good quality, but not the same quality as our process. So we are a semiconductor fab. We use semiconductor processes for etching and machining, lithography and etching. So you have very, very, very high accuracy of the elements and very low roughness.
Thank you.
Yes, thank you. The second question from Moritz, ficonTEC. Moritz, please go ahead.
I have two technical questions, Wilfried. So the first one is, I mean, is there a difference from the material system if you're using silica or if you use silicon from the processing? Can you do different, more complex shapes in the one versus the other, or is that rather similar?
That's a very good question. So so the lens shapes are the same, but since the refractive index of silicon is a factor 2.2 higher than for fused silica, you can go to higher numerical apertures of your laser source. So that means if you have a 0.6 NA, you can handle this with silicon, but it's difficult to do with fused silica, but just because of the refractive index, not because of the lens shape. Then these mirrors that you see in the top right corner, so these are easier to be done in silicon, but we also have a process now to do them in fused silica. And other than that, we use the same processing, the same technology for both materials, so that's pretty much the same.
Okay. Second quick question. I mean, you have also shown structures which have structure on both sides of the material. So how well can you align the top to the bottom surface or the structures of both of them?
But typically, we specify better than 3 microns, plus minus 3 microns. It can be better than this. It can be like 2 microns. But we always specify better than 3 microns, plus minus 3 microns, so in X and Y. So that means, so it for on a 200 micrometer lens or so, it's more than enough, typically accurate enough.
Perfect, thanks.
All right. So let's thank our speaker again. Thank you very much, Wilfried. Let's go back to the presentation of John Earnhardt from OFS.
Let's try this again. Okay. Seeing anything yet?
Not yet.
Just one moment.
Make sure, so you push the button to share the screen at the bottom of the Zoom.
I can do that, huh?
Okay.
I can see. Okay, it's working now. Perfect.
Trying to go to full screen, just bear with me.
You can just push F5.
Yeah, that's what I did. Let's try this.
Maybe you have multiple screens?
No, it's just stuck. But there's no problem. I can share my screen, John.
Okay, let's do that. Yep. Plan B.
Okay, a moment. There you go.
There we go. All right, so again, John Earnhardt with OFS Specialty Fiber. And you'll see in the lower right-hand corner, we've actually got two logos on each of the slides, and that's important for this presentation. So we are a optic company as OFS, and we are owned by Furukawa, which also is active in lasers. So we cover both the active side and the passive side, which makes it life rather interesting when we're providing the passive part to the laser part. So often the fingers are pointing different directions. Next slide, please.
And I'm not in the next slide. I'm in the next slide.
Yep, next slide.
I am already. You cannot see it?
Oh, I don't see it. Okay. Yeah, I must have a bad.
No, it's not seeable. Doesn't see it, Panos.
Okay. Just to understand, everybody else can see my slides, but it's not on. It's only John who cannot see it.
No, we can also don't only see the first slides.
Yeah, we see the first slide, Panos.
Okay, so it's my mistake then. I'm starting again. Can you see it now?
Coming up. Not yet. It's a little bit slow.
Still not yet.
I think you co-packaged too many slides in that presentation, John.
Exactly. I've got a conflict between lasers and fibers.
How many videos?
Panos, why don't you let John try to share his slides again?
You know what I'm going to do? I'm going to try to use. I'm going to go to Adobe and hope that that helps out.
Okay, we can see your cover
faster.
slide.
That was faster.
Yeah. How about now?
We can see your cover slide. Let's see if we can see the next one.
Yes, it works,
Yes.
works.
Yeah.
You just have the blue thing on the screen, which you need to click away on the upper right from reopen close PDF. Thanks.
Yeah, now it's perfect.
Perfect.
All right. Well, thank you for your patience. So we've been involved across many different specialty fiber applications and markets for the better part of 30 years. But specifically in the telecom and datacom space, we work mainly with OEMs and some of whom are actually on this call now. And we've supplied erbium dope fibers, polarization maintaining fibers, low bin loss fibers. Now there's some emerging new fibers like hollow core that we're very active in. Tiger mentioned multi-core fibers. So there's really a broad range of products that we're supplying into the industry. On the other side, Furukawa, so we also have been very active as Furukawa for many years in telecom type lasers. We have a chip fab in Chiba, Japan. We also have a laser assembly and packaging facility, Furukawa owned in Thailand. And most of what we do in terms of lasers is DFB-based technology. Historically, that's been packaged lasers like micro ITLA, tunable lasers. The trend recently has also been to provide chips for integration with silicon photonics. But then in the future, we are also looking at external laser source or ELS modules, and we'll actually be shipping our first samples in June. Tiger showed this earlier, but this is the transition going from copper dominant to fiber dominant on the right. And just an exploded view of the fiber routing. And as Tiger had pointed out, we have a large number of both PM fibers and single mode fibers in the architecture highlighted above on the right. So when we look at this from a fiber optic perspective, of course, there's single mode and PM fiber. And so what we have to worry about from an optical standpoint is what is the mode field diameter? So in some cases, we've got customers who want a conventional sort of 9 micron type mode field diameter. And then in other cases, a customer wants something that maybe interfaces directly with the chip that might be in a 3 micron mode field, and a couple of options in between. Low bin loss is becoming increasingly important as transceiver modules shrink in size and go to QSFP-DD and OSFP. And there will likely be pressure on low bin loss as well in the CPO area. PM fibers, we need to worry about traditional PM properties like beat length and PER and so on. And another area that we have to watch out for is path interference, particularly as you go to these low bin loss fibers. It can become more of a problem, and looking at also matching the mode field diameters. So there's an optical side to this, and then there's also a mechanical side. And we will see increasing pressure as a fiber optics supplier to improve our tolerances. So those could be core clad offset, core diameter, clad diameter. You know, on the laser side, we do a lot of things to improve our power and improve our efficiency. If we don't do things right on the fiber side, we can essentially negate or throw away a lot of that effort. So over time, as the volume increase, there will be more pressure to improve the mechanical tolerances. In addition, the question is what clad diameter? So 80 micron or 125 micron. The initial ELS samples will ship next month will be based on a 125 cladding diameter. But we are certainly seeing pressure for more 80 micron fibers, both PM and SMF, that we're currently shipping for transceiver and other types of applications. In addition, the coating, we're seeing a couple of emerging trends on coating. One is smaller diameter. So on a 80 micron cladding, the typical diameter is approximately 165. We have begun shipping some samples at 135 micron. Again, that's a coating diameter. There was some discussion about thermal issues and solder reflow earlier. So we've also seen more pressure to provide alternate coatings that will survive at least short-term duration of higher temperature with solder reflow, and possibly survive longer-term duration with some hotspots in some of the tight packaging. So on the ELS front, as I mentioned, we'll be shipping next month in June. In this particular case, the ELS is pigtailed. We did see a backplane discussion earlier. That is something that we will make available at a later time. We're looking at either a CWDM style format or 1311 style. It is PM fiber based using OFS PM fiber. And the current output power that we're, and this would be power out of fiber that we're focusing on, is 100 milliwatts. So this is my closing slide. You know, this really is all about a new ecosystem, and I really appreciate that EPIC is pulling together all of our different speakers today. You know, it's interesting, we're approaching this more from a component level, but we've heard people with higher level system integration. And it's going to require a network of all of us to develop the right standards, to design and integrate these new components, and to scale production. And we think we're in a very interesting position as what we call one Furukawa. So the combination of Furukawa active devices along with the OFS passives. And really appreciate the opportunity to speak to all of you today. And thank you for the patience in getting the slides set up.
Okay, thank you very much, John. Yes, indeed, you're right. So the ecosystem is very important, especially at this stage. And actually, Tiger from Senko has already a few questions for you.
Hey, Tiger.
Hi, John. Thank you very much for a great presentation. A couple of questions, but one is Furukawa or OFS working on the pre-aligned PM ribbon fiber for big zero termination?
That is a great question, and that is very much the question of the day. Yes, but as you can imagine, it is very much non-trivial. So we can talk some more offline about that, but you know, that has not come up so far. And what I'll call the packaging of the fibers is definitely a critical part of all of this. You know, we're dealing with a large number of fibers that presents a bit of a rat's nest. So having the right packaging of those fibers, and then a pre-alignment of the PMF. So it's the desire is to have a drop-in solution that will drop into an array or into an MPO style connector. So great question. And if anybody's got great ideas on that, we're all ears.
Maybe by the next event, there's some news, hopefully.
Yeah. Yeah.
Okay. And the second question was about, relative to my comments made earlier about the, there are some changes to the process and operation when it comes to Kobayashi optics, of course, the reflow to 260 degrees Celsius, and also potentially, depending on the applications, you may have to operate at the higher temperature beyond 100 degrees C. And I think primarily it's about the coating of the fibers, but is there any specific materials that you are selling now or in development for such?
Yeah, we actually are selling currently, at least at a prototype level, essentially a mid-temperature dual coat. We've provided papers on this at OFC in the past, and so we are shipping some commercial quantities, both of PM fiber and single mode fiber. So thank you for that question.
Thank you very much, John.
Yep.
Yes, thank you, John, for the very nice presentation. And we go to our next speaker, Moritz Seyfried, the R&D manager from ficonTEC service. Moritz, the floor is yours.
Perfect. Can you see my screen, Ivan?
Yes, it's all good.
Perfect. Great. So yeah, welcome and thank you for the opportunity to present a few slides and also 2 video snippets on what we as a solution provider for the testing and assembly are facing with when it comes to co-packaged optics. First of all, I mean, the picture you have seen multiple times already. So we're having really a lot of fibers entering the main PIC core. And the connection of the fibers, we do mainly see 2 different options. The one is having a passive fiber alignment in case there's a silicon photonic chip with weak grooves. So the passive placement of the fibers is doable. And the second option would be in case we have a silicon photonic chip with an edge coupling, that we use an active fiber alignment, then either with or without additional optics in between. So these are the two options. I will have a closer look in the next slides. However, before looking on the assembly, you may want to have a first check on your idea on wafer level already about the functionality of your photonic integrated circuits. So this is where we're offering so-called electro-optical wafer level testings, by which we can either using the grading couplers from the top or also edge coupled capabilities on wafer level for coupling the light in and out of the chip, as well as then for sure the standard DC and RF electrical contacting. So in case you have verified the functionality of your PIC device with that one, you can do the next step towards the integration of laser diodes. So we learned that either, I mean, there are a lot of trends having the laser source external installed. However, if you're looking for some heterogeneous integration of the 3-5 die into the silicon PIC, we have developed a quite nice technique based on, let me move to the pointer. Based on an infrared imaging or optics using a microscope objective. So we are able to look really through the silicon, because the silicon is, as you know, transparent in the infrared region. And by that, we can really monitor and look at the interface between the 3-5 die and the silicon substrate. And you see kind of two pictures here to the right, where we're really looking through the silicon die. And then when having the 3-5 on a 6-axis alignment stage, we can really lively monitor the position and then align until we have achieved the final position. We have been able to really achieve an accuracy of the die tracking, not of the bonding, but of the die tracking through the silicon in the range of something like 70 nanometers, so for 1 sigma, bringing us into the region where really the direct butt coupling of the 3-5 die into silicon photonic waveguides is possible. And combining that with localized through silicon laser soldering, meaning not only doing imaging from the bottom, but also using laser soldering for the fixation of the two components, it's quite a nice combination. So after this fixation of the 3-5 die to the PIC, you may want to do a second step of functional testing on wafer level or on die level, depending on what you've done before. But then finally we come to the assembly of the fiber. And for the fiber preparation, we have a so-called fiber line machine series, which is also using making use of a CO2 laser to remove the coating from the fiber arrays, or fibers of fiber arrays, as well as then using a higher focused beam to really cut the fibers. And that's what you will see in a quick video snippet here. Really, you see a CO2 laser coming from top and bottom, so from both sides at the same time, removing the coating, as well as then being slightly refocused and cutting the fiber or fiber array into different components. And one example could be you could use that fiber array to bring it into the connectors, then fix it with this UV durable epoxy, and you have the connector already ready on one of the ends of the fiber array. The second side you can prepare in a similar way, and then, for example, use for the passive fiber to regroove assembly process, which is shown here on a picture just taken from Google. So you have the fiber arrays, and when placing them into the regrooves, they are automatically passively aligned, so that you only need to fix them with some kind of coverlet to keep it mechanically in position. And that is exactly the process you see on this small video, which you can find also on YouTube. So definitely there's only a part of right now. Can you still hear me?
Yes, we hear you well.
Oh, okay, so because there's a music to the video, sorry for that. So you can see the fiber array, which is aligned only from cameras from top and bottom. Also from the top, so the fiber array, and then the PIC itself, and then based on machine vision, the fiber array is placed into the V grooves, so that the alignment is done. In that case, the fiber is removed to bring in the epoxy before bringing the fiber back to the saved position. So this is the method using the V grooves. The second approach, which I discussed earlier, is the use of lenses or lens arrays directly aligned and fixed to the edge of the photonic integrated circuits, like I've shown here in a picture from Tyndall. And then using a single mode fiber connector, which also has a lens at the end, a lens array. So then we are widening the beam to have slightly less or looser alignment tolerances, and by that allowing for a pluggable connection of the system. And that is something which we are also developing together with Tyndall at the moment in our labs. So really using the fiber array, including the lens array at the end on the one side. The gripper here is holding a small lens array, and this is one of the PIXApp chips which we're using for the tests. So to couple light in and then in a loop back also out of the chip. And then we can fix the lens array to the chip, and having a loose alignment tolerance for the pluggable or for the connector, which then can be made pluggable at the end. Okay, so far these have been all individual machines, so different machines for different purposes. However, looking into really high throughput concepts, definitely you want to implement everything in a more and more automated assembly line. And this is a picture of an assembly line for the automotive industry, which we have installed in Germany a few years ago. But this is not kind of a fake image, it's really a large assembly line, including multiple input and output feeder, as well as different stations of the assembly. And this is only the hardware so far, but there's also quite a lot of software involved. One side, the software for the process implementation, but we're also setting up a ficonTEC called software part, which allows us to really do a nice interface with KPI tracking, as well as AI or ML algorithms, processes really for process optimization in that whole assembly line. So to increase yield, UPH, and all of that. Okay, thanks. That was a very quick overview about what different aspects we could offer for the COPO assemblies, and I'm for sure happy for any questions.
Thanks a lot, Moritz. Thanks a lot for this informative presentation. Amazing job, really, from ficonTEC. I would like to take the chance also to apologize for before, because it might be the case that I had the technical problem and not John. And do you have any question for Moritz? It seems that we have. I hope it's John. So John, again, I'm sorry before. I think it was my mistake.
No problem. So Moritz, thank you. Very interesting. And to Tiger's question earlier, have you been doing any work with PM alignment in an array format? So taking PM fiber and then locking it across, say, 8 fibers and then fixing those fibers in place?
So we have been working with PM fibers, but I think only with this not 8 in a row. So that's definitely something which is also on the list, because that's becoming more and more important. Also having really not only 1 or 2 fibers, but really a huge array or multiple fibers on one chip. So I also see that what you mentioned earlier, that the interface between fiber and chip, that's kind of also becoming a limit from the footprint. So really having more power or more channels into one fiber may definitely be a good option to go.
Thank you.
Do you have any other question for
Wilfried, maybe?
For Moritz? Yes, please.
Yeah, I had a quick question. So you showed different alignment procedures, Moritz, and giving the talk before from OFS, from John. So when do you need to couple light into the fiber, and when can you use other features for alignment? So I mean, there's active alignment and there's active alignment. So and then there's passive alignment. So when I talk, so for active alignment, sometimes you can use features on the either on the rules or on the MicroOptics itself, and sometimes you have to couple light into it. So is there like a rule, or do you like to have a standard for this to go even to the next step?
That's a good point. I mean, if we really come to fiber to PIC coupling, I think really coupling light, so doing it actively, is quite a preferred way. And it's from the speed point of view, UPH, I think it's not necessarily a bad thing. I mean, okay, if you have the regroove, that's rather simple. Go in and push to the end without for sure having contact. But for most of the other cases, I definitely would prefer having some light in the fibers, at least in the moment, because that also can be, if it's prepared well, quite fine from the cycle time. So if you're going to sub-micrometer accuracies, it's definitely also taking time from the vision and all of that.
Okay.
Thank you, Moritz. Please go for it, Wilfried.
Because we've been, so our clients regularly ask us for adding features, and I think other people in the plenum here in the panelists have the same request. So to do fully passive alignment just with features on the MicroOptics. So some type of ledges, some type of features that are. So I just wonder how realistic you see this, Moritz, or is this just out of the question?
I think, I mean, that if it's really the silicon waveguides themselves, I mean, they are a few hundred nanometers in dimension. So as soon as we're going to some beam expansion, kind of mode size converters, I think that's becoming more realistic. So, I mean, I guess that also your structures are in the micrometer range. So I think that's somehow where we need to be, 1-2 micrometer, but not much more than that. And it's it also depends on the power loss which you have. So we are facing quite a for the quantum applications, for example. I mean, this is becoming even more critical to have a very high coupling yield. So I think that could be difficult.
Okay, yeah, I agree.
Thanks a lot. Thanks a lot. So maybe it's better now to go to the next speaker, and if you want to have to ask more questions to Moritz, you can stay here in the informal session and keep asking questions. So the next speaker for today will be Jörg Smolenski from Nanoscribe. Hello, Jörg. And you're ready as always. The floor is yours. You're only muted.
Yes.
Perfect.
Okay, can everybody hear me? Nice to see everybody, or nearly. I'm Jörg Smolenski from Nanoscribe. I'm the business development manager. First, some introductory slides. So we are now more than 100 employees since this month. I'm not sure if it's going to stay like this till next month. We are hiring again and again. So if anybody is interested, a side note. We have more than 40 years in the business, and we provide 3D printing equipment which then can enable reduced losses, optical losses for fiber to chip coupling. Let's click here. So I will not talk about our key technology, the 3D printing technology. You can refer to our website and then you can have a look at it. So this technology enables basically that we can connect from fiber to chip. So you see here the basic scheme. The idea is that we enlarge a mode field on both sides with collimation lenses printed on the chip or on the fiber. Then we have a larger beam area we can overlap and reduce by this the losses, and the coupling losses and the alignment can be much more reduced in the order of 2 to 5 microns plus minus. So one thing we do is this fiber printing. We can do collimation lenses, focusing lenses, tapers, periscopes. And we have a partnership with Fix in Netherlands for these kinds of lens fiber arrays. So we supply them through Fix if you're interested. Here's an example of the alignment of the fiber array. So we had somebody doing some vapor in the lab and then put a green light through the fiber array. So you can see they're very perfectly aligned. We had very good experience, at least in fiber-fiber coupling. We also have done some fiber-to-chip coupling with focusing elements, but I will show a few results later. On the other side, also we can print on chips. This will be is already available for first tests. So we are looking for people going further with this. So how is it going with printing on fibers? Basically, again, we want to have a wider beam to have relaxed tolerances in packaging, or we can do a small focusing beam to couple into the waveguide, order of 3 microns or 2 microns, for example, focusing spot side of the mode field diameter. That was too fast. I wanted to show a small video. So if this is starting, let me quickly start the video. So here you can see a video shortly of the fiber printing process. On the left side, you see the scheme. So that's for a green fiber array. You have the 8 lenses. We first put in the first and last position coarsely, and then the printing process starts automatically. That's the last position. And now we do the alignment. Basically, we look for tilt and flatness and Z position. And additionally, we also look how is the core light emitting. So we have an illumination unit. So we directly print in the direction of light. That enables these precise parallel beams coming from the fiber array. We do this on each core. We could speed up the process doing it on every second, but we have seen that the tolerances of the arrays required to have a good quality to do it on every core. Similar thing for printing on chips. So the other side, basically. So again, this is from the OCT project. This is a handheld OCT project together with ZEISS and some other partners. Here's again, we do a different technology. We use a confocal module. We can detect precisely with Z and XY, scan the position of the waveguides, and then we can print the optical elements. Can be here again focusing, collimating lens, can be tear mirrors, different optical elements, completely freeform. This is what it looks like. We have very good experience. We can also do simulations for customers for the coupling losses. We have a wavefront propagation in-house software for doing tests and feasibility studies. In general, this enables reduced losses. So, but where do they occur? So here's an example of a fiber-to-fiber coupling, just a scheme. I will not go further in this. In the PDF I supplied, there's some more information on this. So mainly we see that you have Fresnel losses, which is can only become by coating. We have bulk absorption. This is very low with our resins we have. You can have a misalignment of the core on the fiber or on the V groove. On the fiber, we are at 500 nanometer precise to the core. So more precise than the mechanical precision. And then you can maybe have a mode field mismatch, but we have seen that with 10% on 25 micrometer, we are still in the 1 dB range. This is what is shown here in the next image. So we have done here green light fiber coupling tests in-house, fiber to fiber, 25 micrometer collimated over 1.2 millimeter. Can be smaller, can also be less than a millimeter, can be a few hundred micrometer. So we had 5 micrometer for 1 dB lateral alignment tolerances, and coupling was 0.7 per lens and 0.3 for the Fresnel reflection. And here is just a coupling. So you have the fiber array. Let me quickly check. So this is the waveguides, and you have the fiber array on this side, coupling into the 1550 nanometer. And there we had a 1.7 dB coupling per interface loss. So this is all done with our QuantumX line we introduced at the beginning of the year. So for printing on PM or SM fibers, photonic chips, and also on 3D photographies. Now just some images to see what is possible. You have seen this already a little bit. These are the geometries we can do. It's really nice freeform. Again, the aligned beams. See the lenses in this time, these were 5, 4, 6, 7 lenses printed. This is again a special one. We can read freeform, do a fast access, low access collimator directly printed on a facet of edge emitting laser. And now it's coming to the end. So I think I'm nearly in time right now. What can you do for us? Come to us with your coupling challenge. We can help you, or at least try to. I cannot promise 100% success rate, but we have very good results and feedback from our customers. What can we do? We can do the automatic printing, fiber arrays via fix and chips. We can discuss this also. And we can hope to validate our solution for your maybe reduced fiber pitch, because we don't care about the pitch. We align where the fiber is. Thank you.
Okay, thank you, Jörg. That was a great presentation. Do we have any questions for Jörg in the audience? Okay, Moritz, please go ahead.
Yes, one question. You mentioned the tool specifically also for quantum applications. So it's called quantum. So what is the experience with the 4 Kelvin range and the, I mean, if you're cooling it down, your devices?
We have some of our resins have been cooled down to 4K without any major issues. But we have not the data for all the resins. For some resins, we have the values. It has been proven, and for others, we don't. We are missing the information.
But if I would imagine a system of whatever laser diode, you're coupling fiber into a PIC, it's kind of a different material system. So you could imagine that it survives the cooling down to 4 Kelvin.
Yes, this is what a customer from us has done. Yeah.
Okay, thanks.
Okay, thank you. And the second question comes from the European Space Agency. Lion McKinsey, please go ahead.
Hi, Jörg. Thank you very much for the presentation. Just a quick question. Have you done any kind of mechanical assessment of how well your lenses adhere to the surface to which you mount them?
We have not done according to any space-related standards. We have done internally in the lab and with customers, but not to space-related standards. We would like to, so we can talk about that.
I mean, if we talk about, say, Telecordia standards, have you done any assessment to those standards? Or
I need to check with our customers. I have no information on that.
Okay, thank you.
Okay, thank you. Jörg, I'm wondering if Nanoscribe is developing new tools also, like an advanced versions of this of the alignments.
We can talk about it. We can talk about this in a year.
All right, all right. Then make sure you still join our seminars in a year.
No worries. I love these seminars. I will join them. No worries.
Great. We love you too, Jörg.
See you.
Okay, thank you very much. It was a great presentation, and yes, let's thank all the speakers of the day. So this actually concludes our seminar for this time. Let me just share a few thoughts with you right now. And my screen has frozen.
Okay, and since we have again issues today with Zoom, Ivan,
yes, hello, I'm back, but yes, there is something going on with the screen sharing. Let me try again. Sorry for this. Can you see it well now?
Perfect. Full screen mode.
Oh, perfect. It is in a full screen mode. It's not?
We can see it. We can see. Don't touch it. We see it.
Okay, good. So yes, regardless of these technical issues, so we had a great discussion, I believe, today. So we have joined in the room wonderful speakers from Senko, Fraunhofer, Huawei, Nanoscribe, Source MicroOptics, ficonTEC, and OFC. So we have heard about the upcoming challenges in the density increase in the fiber connectors. We have heard about the Fraunhofer's technology for the low energy consumption and low price technology upcoming. We have heard about the 100T co-packaged optics challenge from Huawei. We have overseen the external laser sources and the technologies related developed by OFS. We have heard today the talk from ficonTEC about the electro-optical wafer level testing, and also from Nanoscribe about the quantum X-align and the 3D printing, and what 3D printing can do for the co-packaged optics. So I'd like to just remind you that so we are close to the end of this season in the online technology meetings. So we're here on the 23rd of May, and you might be interested in joining us for the 2 upcoming OTMs on June 13 on the VCSEL technology and applications, and also on the June 27 for the quantum communication and the QKD technologies. After this, we'll jump already in the next season that will start in September, and we'll have even more exciting events for you. Another reminder, so this seminar was possible thanks to all the team of EPIC, and EPIC, the European Photonics Industry Consortium, supports you in technology and market reports, provides you with networking opportunities and access to new markets. We also provide mentorship, HR support, and help with investment. These are the speakers of the event today. We thank them again for supporting us, and EPIC members drive the photonic revolution. Thank you very much for joining us.